Alright, so here's a problem for line charge density. Suppose we have a uniform rod that has a length 2a and that is centered at the origin, and we'll simply assume there is a continuous line charge distribution. And also, if something is not given to you, you will assume continuous uniform line charge distribution, and assuming that the diameter of the rod is small in comparison to the distance r. So this distance r is where our point P is. So assuming that the diameter of the rod is small in comparison to the distance r, determine the electric field at r, at the observation point r, which is, sorry, at the observation point P, which is at a position vector r. Okay, so I drew the figure. Our source or the rod is along G. Okay, so the first, and by the way, you can follow me along or you can pause the video and you can work on the problem. All right, so I'll start this problem with something that is already given to us. If the observation point r is much larger in comparison to the diameter of the rod, then we can treat the rod as a line charge density. So we'll begin with determining our r and r prime. So our r in this case is r, and it is along y. So the unit vector will be along ay or along y-axis, and that is how we write our r vector, which is the observation point. Now our source r prime is at some, let's say, let us keep some random location. Let's say this is where we are trying to compute. Okay, let's say this is our some random differential element along G axis, and for that our r prime will simply be along G, and the unit vector is also along the G axis. Okay, now r minus r prime will be ray minus g s sub c, so that our r minus r prime magnitude is root over r square plus g square. So this distance is r minus r prime. Okay, all right, so now we have r minus r prime. We can use our equation, which is the electric field, excuse me, at r is given as 1 divided by 4 pi epsilon 0 integral rho l times r minus r prime on the numerator, r minus, oops, I made a mistake. This is r times ay minus g a sub c divided by r minus r prime cubed, magnitude cubed. So r square plus g square. When you cube that, that will have power of 3 divided by 2 dot dl prime. So in this case, dl prime, realize that dl prime is simply dg, because we are integrating along the g. Our differential element is along g, so we have to integrate in the direction of g, where our lower limit, this point is at negative a, that point over there is at g equals to positive a. Okay, we'll use this and compute the integral. So let me start by separating the terms, or 4 pi epsilon 0, and let me put a big bracket. I think that will be easier. R a sub minus R a y divided by r square plus c square 3 by 2 dg. Okay, negative minus, forgot the integral, minus integral negative a to positive a. So there is of course g is sub g divided by r square plus g square power 3 by 2 times dg. Okay, so these are some standard integrals, and the solution for these standard integrals are given in your equation sheet. Okay, for this first integral, let us check our equation sheet. And that is integral 12. Okay, so r comes out of the integral. We can also take out a sub y out of the integral, and the result of the remaining part, dg divided by r square plus g square power 3 divided by 2 will be 1 divided by r square g divided by r square plus g square minus, okay, for the second integral we have to use integral number 13 from the table of integral, and the result for that one will be, so a sub g comes out of the integral. The result for that can be, okay, I think I forgot something on the first integral, that is the limit for the integral negative a to positive a. Okay, now come back to the second integral, and that will be 1 divided by r square plus c square. So limit is negative a to positive a, and I'll simply use a different kind of bracket. Actually, I was looking at the integral table and it says this should be negative. So negative and negative should make that positive. Okay, I think we are good to go. So let us move to our next step. Rho sub L divided by 4 pi epsilon 0 a sub y, this r and that square will cancel, so we'll be remained with a sub y divided by r, and I will apply the limit, which gives me a divided by r square plus a square. Okay, ideally I'll have a negative, but when I replace g by negative a, it again becomes positive. So we get r square plus a square for the second term as well. And this term over there stays as a sub c. Okay, applying the first limit, 1 divided by r square plus a square minus 1 divided by r square plus negative a square, which is, excuse me, negative a square for there, which is again a square. So this term will cancel, and finally we get okay, we get 2a from there, so cancelling that we get a times rho sub L divided by 2 pi epsilon 0 r, and also that r square plus a square term, and don't forget the unit vector, which is a sub y. Alright, so that is our result. So this is our E at the observation point, and I should not forget that E itself is a vector. Okay, I did put the vector up top. Okay, now let us consider a very special case. Okay, let me write special case. If the rod is infinitely long, then the length of the rod goes to infinity. Okay, and in that case the electric field can be written as follows. So limit a goes to infinity, rho sub L divided by 2 pi epsilon 0 r square plus a square times a y. Okay, so remember in this case we have to rewrite this as, so rho L 2 pi epsilon 0 r, this a goes to denominator and inside the square root, so that becomes r square divided by a square plus a square divided by a square will be 1, because everything is inside the square root. Okay, now we are ready to go and apply the limit, and when you apply the limit, this term over there becomes 0. So square root of 1 is 1, and we get E at r is rho L divided by 2 pi epsilon 0 r along the y direction. So that will be the electric field when the rod is infinitely long. But for a finite rod, the electric field will be given by this result. Alright, that's all for this video.